Good afternoon. We will continue today solving examples from the conservation of energy. So in today's lecture, we will also do the work calculation by friction. And if we have time, we'll introduce the power. So today's lecture from textbook sections 7.5 and 7.7. In next lecture, we will be studying the momentum, the conservation of momentum, and momentum in collisions from sections 8.1 and 8.2. Okay, so let's start with this example. In this example, we have a girl swings back and forth in a playground swing. The maximum height she reaches is 2 meters above the ground. At the lowest point in her swing, she is 0.5 meters above the ground. What is the maximum speed of the girl on the swing? And at which point in her path does it occur? So, based on our understanding of the conservation of energy, we know that the highest, the greatest potential energy we have. The lowest, the least gravitational potential energy. So we also know that since the girl is stopping at this point, which is the highest point, its kinetic energy right at that point is 0. So in other words, I only have gravitational potential energy at the highest point, no kinetic energy, while at the lowest point, 0.5 meter, I have gravitational potential energy and kinetic energy. So this tells me that right at this point, I have the lowest gravitational potential energy, which means I have the highest kinetic energy. If I have the highest kinetic energy in the whole path right at this point, this means I have the highest speed as well, because we know that the kinetic energy is half mv squared. So if the kinetic energy is the highest, then the speed here is the greatest as well. So at 0.5 meter, I have the highest speed among all the points within that path. Now, when it comes to calculating this speed, we will do it this way. So if I am to draw the girl right there at the highest point and at the lowest point, and I put my coordinates x and y this way, such that this is 0.5 meter and this one is 2 meter. Now, the speed here is known, 0. I need to calculate the speed here using the conservation of energy. So if I apply the conservation of energy at the initial and at the final, so let me call this one point A and this one point B, then I have EKA plus EPA equals to EKB plus EPB. So since the speed is 0 right at point A, then I have EKA half mv a squared. So if I am to call this one now VA, just for simplicity, and this one is BB, then I have VA here is 0, which means that EKA is 0. What about EPA? M times G times YA. So if this YA is 2 meter, then I have EPA equals to M times 9.8 times 2. Or EPA is 19.6 M. This is joules. So that's at point A. At point B, I have EKB equals to half M BB squared, and this is what I want. This is joules. And I have EPB equals to M times G times YB, and EPB M times 9.8 times 0.5. EPB is 4.9 M joules. So if I apply now the conservation of energy, I get, let me write this down, EPA plus EKA equals to EPB plus EKB. I have EPA 19.6 M. I have EKA as 0. I have EPB as 4.9 M and EKB as half M BB squared. So you can see that I have M everywhere. I can divide by M to get rid of the M, and then I will end up with half BB squared equals to 19.6 minus 4.9. And then EBB is 5.42 meter per second. So this is how we can calculate the speed using the conservation of energy. And as you saw, the mass, this speed was independent of the mass. We could cancel the mass out without affecting the speed. So the speed here is indeed, in this lossless system, this ideal system is independent of the mass of the object. Okay, any question about this example? No questions? Okay, so we'll move on to the next example then. In this example, we have a young girl wishes to select one of the frictionless slides, playground slides illustrated below, to give her the greatest possible speed when she reaches the bottom of the slide. Which of the slides should she choose? Now, keep in mind that the conditions are the same for all the slides, which means she's starting from the rest at the top of the slide. All the slides have the same height, 2.5 meter, and she would be reaching the same level at the bottom of the slide. So which one do you think would give her the greatest possible speed? Is it A, B, C, D, or it doesn't matter? All of them are the same. All of them are the same because you need to look at from the conservation of energy point of view. So if she's starting at rest, starting from rest, this means her speed at the top is 0, which means her kinetic energy is also 0. Same height, this means that its gravitational potential energy is the same for all of them. And this is the maximum energy she has. And then right at the bottom, she's reaching the same level, which means that the gravitational potential energy is the same at all those positions right at the bottom of the slide, which basically makes the kinetic energy also to be equal. So if the kinetic energy is equal for all of those, this means that the speed is also equal. So the answer is E, it does not matter. Now let's look at this example. In this example, we need to use energy methods to solve the following problem, which is a penguin slides down a frictionless iceberg from a vertical height of 5 meters. If the penguin pushes off, giving himself an initial speed of 0.2 meters per second, what is his speed at the bottom of the iceberg? Now, here we have the penguin giving himself an initial speed. This means he also has a kinetic energy right at the top of the iceberg. His kinetic energy is not 0. He's not starting from rest. He has an initial speed. This means he has a kinetic energy. And he is at the height of 5 meters. So he also have this gravitational potential energy. So we will solve this problem first by defining those 2 points. So here, this is my X. That's my Y. So if I am to call this one point A, in point A, I have VA equals to 0.2 meters per second. I need VB. I have the height here, YA as 5 meters, while YB is 0. So if I am to apply the conservation of energy, I have EPA plus EKA equals to EPB plus EKB. EKA is half MBA squared, which is half M 0.2 squared, and then EKA is 0.02 M, and this is joules. This is the kinetic energy at point A. The gravitational potential energy at point A is EPA, which is M times G times YA, M times 9.8 times 5, then EPA is 49 M. This is joules. So that's at point A. At point B. At point B, we have EPB equals to M GYB, and then This is why V equals to 0, and that's why EPB is 0. We have EPB, EKB equals to half MBB squared. And this is what we want to find. So applying the conservation of energy, I have 49 M plus 0.02 M equals to 0 plus half MBB squared. So M cancel, I will end up with BB equals to 49.02 times 2. .9 meter per second. So the only difference here that the penguin has a kinetic energy right at the top that we had to include in our calculation using the conservation of energy. Now the second part, part B, says the following. If the penguin hits a level patch of lichen at the bottom, how far from the base of the iceberg does the penguin slide before coming to a stop? The coefficient of kinetic friction between penguin feathers and lichen is 0.22. So the penguin's gonna reach the bottom of the iceberg, acquiring a speed along the horizontal direction that is 9.9 meter per second. The coefficient of the kinetic friction is 0.22. Then this force is going to act on the penguin, causing him to decelerate or apply an acceleration in the opposite direction of the motion, causing him to slow down till he stops. So the speed right at the end of the displacement would be 0, which means his kinetic energy would be 0, right? So we need to calculate that distance, how far from the base of the iceberg does the penguin slide before coming to a stop. So what we have here is we have a mu k 0.22. So basically here, if I am to draw the free body diagram, and I have the penguin, gravitational force, normal force, I have the kinetic frictional force, and then he is going to go through a displacement before stopping. So let me call this BC 0, while VB here is 9.9 meter per second. So the frictional force is the only force applied on this penguin, causing him to slow down, coming to a stop. We need to calculate this displacement. So how can we calculate the displacement? Any idea? Okay, so one of the ways that we have seen before is to apply the work energy theorem. In work energy theorem, we have the exerted work W equals to delta EK. And in this case, we have W equals to EKC, which is the final, minus EKB. Since the penguin is coming to a stop, VC equals to 0, this means that the kinetic energy at C would be 0, right? Then I have here W equals to minus EKB. So, what is the work? The work, by definition, is the magnitude of the force times the magnitude of the displacement times the cosine the angle in between the force and the displacement. So W is Fk magnitude times delta R magnitude times cosine. Can somebody tell me what is the angle between the displacement and the frictional force? 180 degrees, right? So this is 180 degrees equal minus, what is the kinetic energy at B? Half mvv squared. I need to calculate the displacement. Keep in mind that I need delta R. If I need delta R, I need to calculate the frictional force. Frictional force is mu k Fn. And Fn can be calculated through applying a Newton's first law along the y-axis. So I have here sigma Fy equals to 0, which means Fn minus Fg equals to 0, and Fn equals to Fg equals to mg. So Fk is mu k times m times g. Take this one and substitute it in here. I have mu k times m times g of delta r. Cosine 80 is minus 1 equals to minus half mvv squared. M with the m and the minus with the minus, then delta r is vb squared divided by 2, which comes from the half here, times mu k times g, or delta r is 9.9 squared divided by 2 times 0.22 times 9.8. Delta r equals to 23 meters based on the significant digits we have in this problem. So the displacement is 23 meters. We calculated the displacement from the work energy theorem. Any question about this problem before we move on to the next one? Yes. Let me come closer to you to hear you. cosine 180 degrees is -1. So we put, so yeah, I put -1 instead of this. Any other questions before we move on to the next one? Okay, so in this question we have a marble that is released from rest, as you can see, from a vertical height h, rolls down the side of the ball of a ball. Now this ball is, as you can see, symmetric, which means that the left side is the same as the right side, and it's a frictionless, has no friction. Now, based on your understanding to the conservation of energy, are you expecting this marble to reach the same height once it starts rolling up, or less height, or greater height? Remember, we released it from rest. So what do you think? Is that marble going to reach the same height, less than h, or greater than h at the other side? It's a frictionless, it's symmetric. Yes. No frictions. No frictions. Same height. Based on the conservation of energy, if we are starting from rest, this means this gravitational potential energy is our total energy right there at the height of h, and then rolls down, reaches the bottom where all the energy is transformed into kinetic energy, and then goes up again such that this kinetic energy will be transformed into a complete gravitational potential energy, because it will have to reach a point where its speed will be 0, right? Which means the same gravitational potential energy will be achieved at the other side if the system is ideal, frictionless. But if we have a friction in the system, then what's going to happen? Are we going to be able to reach the same height? No, because some of the energy during this path will be wasted in the friction, which means this is going to be affecting the maximum gravitational potential energy that my marble is going to reach, which basically translated into less height. So it is the same. However, if there is a friction, then it should be less. Now let's look at this example here. In this example, we have a penguin pushes with its feet to gain an initial speed of 1 meter per second and slides 0.5 meter. So he gave himself an initial speed of 1 meter per second. That initial speed of 1 meter per second allowed him to slide for half a meter. Okay. Now the question is, what happens if what is the speed if this penguin, same penguin, managed to slide for 2 meters? How much do you think the speed he gave himself? Now we'll have to, calculate that. It's not a straightforward thing, but it's a very useful example for you to give you an idea about the ratio, the relationship between the speed with respect to the displacement. So in order to solve this problem, we will start with the free body diagram for this penguin. Now, this penguin has a gravitational force. Normal force. Kinetic frictional force. And he managed to go a displacement of delta R. I will call this one delta RA. And this is my displacement. So let me put the coordinates here. So that's for case number 1. For case number 2, we have the penguin, same normal force. It's the same penguin, same mass, same friction, which means the kinetic frictional force is the same. The normal force is the same. The gravitational force is also the same. However, because of the greater initial speed he gave himself, now we have a greater displacement. So this is my delta RB. I need to find the relationship between RA and RB. So what do I know here? I know V naught A and this is VA equals to 0. VB equals to 0, and this is V naught B. So this is case number 2. So from case number 1, if I apply the conservation of energy, EK initial for A plus EP initial for A equals to EK final for A plus EP final for A. So here, at this point, let me delete this. I wanted to say the work is delta EK, which is the work for A equals to EK final for A minus EK initial for A. And the work here is Fk times delta RA times cosine 180 degrees equals to. Now, the final kinetic energy for A is 0 because VA is 0 at that point. So the final point is 0. So I have here minus half m v naught a squared. Is that right? This is similar of what we have done earlier. I'm just repeating ourselves here. So we have minus cosine 180 minus fk times delta Ra equals to half m v naught a squared. This is for case number 1. So what are you expecting case number 2 to be? Yes. From cosine 180. Cosine 180 is minus 1. So this is for case number 1. What are you expecting case number 2 to be? The same. Except, so this is case number 1. For case number 2, I have minus fk times delta Rb, the same kinetic frictional force. However, the delta here, the displacement here will be delta Rb equals to minus half m v naught b squared. Is that right? Same thing, except applying the work energy theorem. I have displacement here for A, I have displacement here for B, I have V naught, initial speed for A squared, I have initial speed for B squared. Both of them, they have the kinetic energy at the final destination equals to 0 because they're coming to a stop, right? Now, if you divide this equation, let me call this one equation 1 and this one equation 2. If you divide 1 by 2, what do you get? Divide 1 by 2. I get minus fk times delta Ra over minus fk delta Rv equals to minus half m v naught a squared divided by minus half m v naught b squared. This is going to cancel, this is going to cancel, so it will end up with delta Ra over delta Rb equals to v naught a squared divided by v naught b squared. Or v naught b squared equals to delta Rb divided by delta Ra times v naught a squared. Or v naught b equals to square root of delta Rb divided by delta Ra times v naught a. So if you substitute now delta Rb with 2, delta Ra with 0.5, and v naught a with 1, you would get 2 meters per second. So what did we understand from this problem? We understood that for the same mass, for the same friction, if you increase the speed by 2 times, the displacement that you're going to get in sliding would be 4 times. Again, for the same mass, for the same surface, for the same friction, if you double the speed, if you double the initial speed, the displacement will be 4 times. Is this clear? Any question about this example? Questions? No questions? Okay, so let's move on to the next one. And maybe the last one for today, and the last example also of conservation of energy. So in this example, we have a box of apples that has a mass of 22 kilograms. Slides down a ramp inclined at 44 degrees to the horizontal. The friction force on the box has a magnitude of 79 in Newton. The box starts from rest and slides 2.5 meters along the ramp. Determine the work done by friction. So we have a box. This box has a mass of 22 kilograms and is facing a friction. This box slides all the way down. He slid 2.5 meters. He started from rest. Starting from rest means zero kinetic energy, right? So we need to calculate first the work done by friction. So the first thing we need to do is draw the free body diagram, put the coordinates, so we have here the gravitational force. We have the normal force. And we have the kinetic frictional force. We're starting from rest. So let me put here first, we have the mass of 22 kilograms. We have theta, 44 degrees. We have Fk as 79 newtons. We have delta R as 2.5 meters. So if I'm to draw a line parallel to the horizontal line, just to define the angle, I have 44 degrees here. So this one is the complement, and this one is 44 degrees. So that's theta here. I need to calculate, here is the displacement. So again, I'm starting from 0. I don't know the final speed at the end, but I know that the displacement here is 2.5 meters. This is delta R. Okay. If I want to calculate the work done by the friction, then it would be W equals to only the friction. It will be Fk times delta R times the angle 180 degrees. So cosine 180 degrees. Then the work is 79 times 2.5 minus 1. And this one is the work due to the friction is minus 197.5 joules. the work due to the friction is always negative. It's a lost energy, right? However, part B is asking us to calculate the thermal energy produced by this friction. The thermal energy is always the negative of the work done by the friction. So here will be minus W, and thermal is 197.5 joules. So this is the thermal energy produced. So if you look at it from the friction point of view, it's a lost, right? It's a lost energy due to the friction. However, the thermal energy here is produced energy due to this friction. So the thermal is always the negative of the work of the frictional force. C, the box's final speed. Use conservation of energy. We need to calculate the box's final speed. So how do we do this? Using the conservation of energy. Now, the system is not a lossless system. The system is a lossy system. There are losses that I have to account when it comes to the conservation of energy. So you need to think about it as you have an energy at the beginning of the path. This energy is going to see some losses due to the friction. So it will end up with a less energy due to this loss. So you can look at the energy at the beginning of this path equals to the thermal energy produced plus the remaining energy. So in this case, I can say now that if I am to write the conservation of energy formula here, I should write, this is point, let's say point A, and this is point B. I should say EPA plus EKA equals to EPB plus EKB plus E thermal. So the budget of the thermal is coming from the total energy before the friction happens. So in this case, I'm starting from rest, which means EKA is 0. I'm reaching my reference here, the floor. In this case, that level has a gravitational potential energy of 0. So in this case, I need to look at a different coordinate where my box here reaching the level of 0. And now so the height here can be calculated from this triangle here. So this is the triangle. If I'm to draw the triangle, this is 44, right? And this is 2.5. So this is the opposite. So I have here sine 44 degrees equals the opposite divided by hypotenuse. Then this opposite equals 2.5 times sine 44 degrees. And this opposite is sine 44 times 2.5 equals to 1.74 meter. So now this is my height that I need to calculate the gravitational potential energy at. So EPA is M times G times YA. EPA is 22 times 9.8 times 1.74. EPA is 375.1 joules. What about EPB? EPB is 0, right? I have the box reaching the bottom, which is EPB is 0, since YB is 0. What about EKB? This is what I want. I want to have MV B squared, or EKB, half times 22 VB squared. This is what I want. Choose. I want the VB. So what else? And I know the thermal. Now let's substitute. EPA is 375.1 plus 0 equals to EPB is 0 plus half, which is 11 times VB squared, plus the thermal, which is 197.5. Now, if you rearrange, so what do we have here? We have BB squared equals to 375.1 minus 197.5 divided by 11. Is that right? 375.1 minus 197.5 divided by 11, square root is 4 meter per second. dB is 4 meter per second. Okay, so let's stop here.